Hello, 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 ladies and gentlemen, and welcome back to question number 3 on the 2010 Galois paper. So we've got 3 parts to question 3, A, B, and C. Question A, solve the system of equations algebraically for x and y. So we've got a system here. So there might be some, there might be many, there might be one, there might be no pairs x and y that satisfy both equations. It's our job to figure them out. We have to remember that if there is a pair of solutions, they satisfy both equations at the same time. X plus y equals 42. We also have to show our work, maybe explain our intuition on certain parts of it. Yeah, so I got those copied correctly. So what I'm going to do is call one equation 1, the other equation 2, and if I find more interesting equations later on, I might introduce a 3 and a 4. It makes things very clear when I start saying things like subtract equation 2 from equation 1. Okay, what does that actually look like? So we're going to write down equation 1 and write down equation 2. Now you might not be comfortable subtracting equalities until you realize you've done it your entire algebraic life. When you see something like x plus 5 equals 7 and you subtract 5 from both sides, what you're really doing is subtracting the equation or adding the equation. Let's stick with subtracting. What you're really doing is subtracting the equation 5 equals 5 from both sides. And as long as both have an equality, you're allowed to keep the equal sign in the end. Okay? So, you know, this isn't the most outrageous idea, but if you're new to it, it takes a little getting used to. Although, hopefully, if you're writing this contest, you're not that new to it. But x minus x is 0 x's. Y minus negative y is 2 y's. And 42 minus 10 is 32. And from here we divide by 2 on both sides, and we get y is equal to 16. Now, we can either take that 16, plug it back in, and solve for y. Y will be 26. Or you could just say something like add equation 1 and equation 2, just to give us a little more practice in case we're not comfortable manipulating these expressions. Now, if I add them, 2 x's, I'll get 2x. A y plus a negative y is 0 y's. We'll get 52 here. Divide by 2 on both sides, you'll get x is 26. And we might just make a little therefore statement. 26, 16 is the only solution to this system of equations. Something like that. Now we're all set. Okay, so that's A part, not particularly difficult. B part. Suppose that p is an even integer and q is an odd integer. We have no idea which ones they'll be. Explain why the system of equations x plus y, x minus y, so x plus y is p, x minus y is q, has no positive integer solutions. Okay. Well, this looks an awful lot like the expression we had in A. The only difference is instead of 42 and 10, we have p and q. Main difference being, well, the top number is still even, but the bottom number is not even anymore. Now it's odd. Okay, but we can still sort of progress in the exact same way, and we'll find out at some point, hopefully, as long as we keep in mind that p is even and q is odd, we'll hopefully find some point where our solution, in terms of p and q, can't be an integer, and we'll know that for sure. So we might do something like, well, subtract 2 from 1. The exact same way we did it last time. There's no reason to change what we're doing. The equations are essentially the same. The only thing that's different is the numbers on the right side of the equal sign. And you don't have to do, what I'm doing is called Gauss-Jordan elimination. You don't actually have to do it this way. You could, if you know about matrices, set up a matrix, invert it and things like that. But most people in grade 10 haven't seen that, so we're not really going to go over it. So once again, we're going to get 2y, and that's going to have to be equal to q minus p. So my solution will be y is p minus q over 2. And this is the problem. Okay? P is even, q is odd. What happens when you subtract an odd number from an even number? You get an odd number, and p minus q over 2 is then not an integer. You can only divide evenly by 2 if you're looking at an even integer. Now, they wanted me to show you just can't have pairs of positive integers, or did they want to show that both x and y can't be? No, just no positive integer solutions. I don't know why it has to be positive, because the same reasoning will still work, even if we're looking for negative solutions. They still won't be integer solutions, but okay. But that's about it. We just argued down to a point and we said, aha, this can't be an integer. And you could have done it the same way. You can get x is p plus q divided by 2. That is also not an integer. You're only going to get integers if p and q are both have the same parity. Either they're both even or they're both odd. So there we go. And now we can try and read C, but somebody drew a line through it. All right, C, the last part here. Determine all pairs of positive integers, x and y that satisfy the equation x squared minus y squared is 420. 420. Okay. So, what I would do here, I recognize that this is a difference of squares. But we can, in fact, factor the left-hand side. And so now, if, and this is explanation that we need to write out, if x and y are positive integers, and now I'm realizing why they had me say positive integers in part B, because we're about to use it, then x plus y, x minus y are factors of 420. Now, I just said factors. I didn't say positive factors. I can confidently say that x plus y is positive. And that means that x minus y, which is 420, a positive number, divided by x plus y, a positive number, is also positive. So they are positive factors. So they're both positive factors of 420, and their product, as we can see here, is 420. So we ask ourselves, well, what are the factors of 420? So we can have, what would be the easiest way to write out these factors? I don't want to just start guessing randomly. So 420 has a factor of 2 in it, leaves 210. That has a factor of 2 in it, that leaves us 105. That has a factor of 5 in it, that leaves us 21. Which has a 3 and a 7. Okay, so 420 is 2 squared times 3 times 5 times 7. This is technically 3 to the 1, 5 to the 1, 7 to the 1. If you haven't seen this, this is a pretty nice trick. How many factors do we have? We have 2 plus 1 times 1 plus 1 times 1 plus 1. We just take the exponents of different primes. So we'll get 3 times 2 times 2 times 2. Which is 24. So we're looking for 24 factors. And now if I start making my list, I'll know if I've left something out. So 1, 2, 3, 4, 5, a 6, a 7. Wow, that's a lot already. What's the next one? 10, I guess. And so far we've got 2, 4, 6, 8 of them. 12 is a factor. 15 is 14 is a factor. And as you write these out, and I'm just trying to write them out in increasing order, you can get the corresponding factor. We're going to need them anyway. 1 and 420 multiplied to 420. You get 210 here, 140 here. If I divide it by 4, it'll be 3 times 5 times 7, so that'll be 105. If I divide it by 5, that'll be 84. Divided by 6 will be 70. Divided by 7 will be 60. Divided by 10 will be 42. Divided by 12 will be 35. It helps to have these prime factors over here. Divided by 14 will be 30. Divide it by 15, and it'll be 28. Now we've got 2, 4, 6, 8, 10, 11. I'm missing one more factor. It's got to be greater than 15, less than 28. 21 and something. 21 and 20. There we go. Okay. So there we go. We have all these pairs. Now, just because we have all these pairs, and so 12 pairs, doesn't mean that we get, so our x plus 1s might be 420, my x plus y's might be 420, my x minus y would then be 1. But does that necessarily give me a positive integer x and y when I solve? And that's what B part is telling us. B part said if you got x plus y, x minus y, we've got x plus y and x minus y in this question, and x plus y is even, x minus y is odd, you don't get a positive integer solution. Okay? So we can use that knowledge and sort of simplify our process or our counting. Now, I wouldn't necessarily just say, well, by B part, these ones will work, these ones won't. What you could do, so here's one thing you could do. You could say, well, we got 4 cases. B gave us the idea for this. And you could say this has positive integer solutions if and only if P and Q are both even or P and Q are both odd. Now, this is a nice, true statement, but if you're going to use it, you can't just say, well, part B fits the pattern, so it must work exactly as I say. No, you're going to have to prove it. Okay? And, you don't have to be super strenuous when proving it. You can just say, well, one can check that P plus Q over 2 is going to be my X, P minus Q over 2 will be my Y, and if P and Q are both even or both odd, these are the only times that you'll get positive integers there. That's fine. That would be a fantastic way to do it. And then you could go back to our list and run through and say that, that's even and odd. These are both even, so that one's fine. That's even and odd, so no. That's even and odd, even and odd. In fact, you'll always get at least one that's even. So you only have to look for, are both factors even? So that's not going to work. That one will work. Not going to work, will work. Not going to work, not going to work. And so then we see, we've only got 4 pairs that actually work. And that's a fine way to do it. I think it's clever, it's slick, it's nice. Another way to do it, and I think I'm going to need a little more space here. Another way to do it is just sort of make yourself a very lengthy chart. One thing you would probably want to say before starting this chart is x minus y is positive, so x has to be greater than y, and so x plus y is greater than x minus y. It helps you figure out which factor is which. But that's a separate way to solve it, and then just sort of running through the list. But another way you could do it, if you really wanted to show your work, is I would make a little chart here. get your x, get your y, and then ask, are they both positive integers? So you get 1, 420, and so x will be 420 plus 1 divided by 2, so that'll be 421 over 2, and automatically you can say no. I don't need to figure out that y is 419 over 2. But you can do it this way too. Obviously this is going to take a little longer, and I don't recommend it. But if you, you really can't make the connection with B part, that's fine. No one insists that you have to do things exactly the way that I do them. 210... 70, 60, 42, 35. Which one was paired up with 5? Oh, 84. Okay. And so you can get 212, so x will be 106, and y will be 104 in this case. And so those are both integers, and now I do have all the pairs. Now, did they ask us for all the pairs? Oh, they actually did. They did determine ask for determine all pairs. So this is a nice table, and I'm able to read off my pairs right away, as opposed to that last method where I was able to count the number of pairs, but I'd still have to work them out this way. 109 over 2, and then 101 over 2. 89 over 2. 79 over 2. Here, 76 divided by 2 is 38, and then 64 divided by 2 is 32. 67 over 2, and then 53 over 2. 26, oh hey, 42 and 10, that's one that we already did. That's pretty nifty. 47 over 2, 23 over 2. 41 over 2, 1 over 2, and 15 plus 28, so that's 38 plus 5, so that's 43 over 2, and then 13 over 2. So, as predicted, 1, 2... Did I miss one? I feel like I missed one. 14, never did 14. Should have copied my list a little better. Let's give myself a little bit more space here. Six, 7, 10, 12, 14, 15, 20. So 12 went with 35. We got 42, 60, 70. What was with 14? Oh, 30. And that did give us an integer solution, so that'll be 44 over 2, which is 22, or 16 over 2, which is 8, and that is a positive integer. 38, 32, 67 over 2, 53 over 2, 26, 16, and that was 47 over 2, 23 over 2. There we go. We have all four solutions. So x and y is going to be either 106, 104, or 38, 32, or 26, 16, or 22, 8. And there we go. So that wraps up the question quite nicely, and that's the last bit of question number 3. So we've just got one more question to go, and that'll be question number 4. So take a little break, take a little breather. I will see you guys in the next video for question number 4.